But then with no further ado, I should introduce Ed Lockhart, who's a research engineer at DeepMind, and he has extensive background in lots of cool areas such as neural speech synthesis, relational representation learning, and reinforcement learning. He's worked on a lot of high-profile things at DeepMind as well, such as mu0. But the thing that he's going to talk about today, which is a good fit for this particular symposium, is OpenSpiel, which is a really cool benchmarking and suite of methods that I'm really excited to hear more about. So go ahead and take it away, Ed.
Great, thank you. For people who weren't here earlier, there is a collab to go along with these slides. I'll just put the link there in the sidebar. So if you want to open that up, you should be able to execute some code, but don't feel obliged to. I will execute it all for you as well. So I should say, first of all, that I'm the only person talking, but OpenSpiel is a work of very many hands. Some of them are here. One thing we're particularly pleased about is we've had a number of really high quality contributions from people outside of DeepMind or Google, some of whom are named here. And here are some pictures of some of the great contributors. This slide actually was some time ago, so there have been people since then who are not on it, for which I apologize. But the key message is there are lots of people. So let's start by just explaining what I'm going to talk about. So first of all, why did we create OpenSpiel in the first place? What's the point of it? I'm then going to give a fairly high-level overview of the API, and then we're going to walk through a couple of examples of using OpenSpiel and implementing a CFR algorithm and a very simple reinforcement learning algorithm. So that's the plan. If we manage to do all that in an hour, I'll be pretty pleased, but we shall see. So first of all, what is it? Why did we create it? So it's an open source framework for research on RL search and planning in games. So a key thing here is that it's intended to serve multiple communities who maybe have different terminologies and different libraries in the past. You can see here on the right some of the games that we've implemented. They include really big games like Go. I should emphasize that AlphaGo does not use OpenSpiel, but some of our research at DeepMind certainly does. Also things like backgammon, which are big games, but also lots of really tiny games that are really useful for exploring algorithms in the small. It's mostly in C++ with interfaces and algorithms in Python. We also have Go, that's Go the language now, not Go the game, and Julia interfaces on top of it. We used to have a Swift interface, but we recently retired it because unfortunately Swift for TensorFlow is now a dead project. So we're no longer doing that. But Go and Julia are definitely vibrant. We have lots of games and lots of algorithms, and we very much welcome people contributing more. I'd say we probably get more speculative contributions of games than algorithms, but we're very welcome to do either kind of contribution. In terms of the kinds of games, this graphic on the right was something that we produced for the blog post when we first publicized it. So we're talking card games, board games, this kind of thing, these sort of abstract games. Any number of players, zero-sum, cooperative, general sum, either perfect or imperfect information, and we also include simultaneous move games in the class of games that we support. Right, I'm going to give a brief tour of what's where. Hopefully you can see this. So this is the GitHub. It has, as you can see, OpenSpiel itself is in here. Most of this is C++ code. There is also some Python code here where you can find, for example, algorithms in Python. There you go. There's an AlphaZero implementation, PSRO, CFR, and so on. Also, I can show you the contributors that we have. We're particularly pleased to have so many great external contributors. There's one and there's no one. As you can see, we have a large number of contributors, which we're very pleased about. And then have a look at the games. Here's a list of the games that we have at the moment. As you can see, they have varying levels of testedness. Essentially, the ones that have green blobs next to them are ones that we've used for our research internally, and we're pretty confident they're correct. The other ones are generally not used for research, and so we think they're right, but there may be bugs. In any case, contribution is very welcome to fix them. There you go, there's a list of games. And then lastly here, a list of some of the algorithms that we have implemented. So in most cases, the way we've done this is we've implemented exactly the same algorithm in both C++ and Python. And the code for C++ and Python is very similar to each other. The reason for that is that we expect that most people will want to do initial investigations in Python because it's easier for most researchers to write in Python, and it's to be a bit iterative that way. But then if you want to run stuff at scale on a large game, then C++ is clearly going to be a lot more performant. So if you're taking an existing algorithm and tweaking it, you can start by tweaking the Python version, and then when you have something you want to run at scale, then you can take the C++ version and apply the same tweaks. Off you go. So that's why we have these kinds of parallel implementations of most of our algorithms. And again, there's a list of them. You can see that 10 in the previous slide was a significant underestimate. So there we have, a lot of algorithms. I should probably say here that internally at DeepMind, we use OpenSpiel for basically all of our research in this area. So all of the papers that we're publishing, the algorithms corresponding to those papers will be published pretty soon afterwards. Okay, that was a very brief whistle-stop tour of the GitHub. What's there? I'm sure you can look at it in more detail. I'm just going to do a brief showcase of the kinds of things that are available in OpenSpiel, as well as these games. So you can have visualizations of game trees. This is Coon Poker. We'll come back to that later. This here is some visualizations of the dynamics, kind of learning trajectory, the replicated dynamics. The main point of me showing you this is to say that if you use OpenSpiel, you get these kinds of things for free, and they make your papers look very much better. So, and here again is another replicated dynamics. And also from a debugging and investigation point of view, OpenSpiel comes with various tools. But, here we're looking at the implementation of dark chess, which is an imperfect information chess variant that has recently contributed by an external contributor. Thank you. And what you can see here is a fairly sophisticated visualization of the current state of the game, and also the game tree over on the right, and the representation that's used for the neural network. So you get all these kinds of things to investigate games that you might be interested in. And then lastly, why do you do this at all? So the main motivation is general algorithms. So the Atari learning environment is a kind of motivating example for us here. So that was is a suite of a large number of games, and the idea is that people write one learning algorithm that then can be tested on all those different games, and the different games have different kinds of challenges. So some of them are exploration challenges, for example, and some of them are more have some memory component to them, for example. So we wanted to do something similar. So you write your algorithm once, and then you can test it on a large set of games that may have different challenges, and take into account all of the kind of standard common benchmark games. That's what we wanted to get to. And why does games make a difference? Well, there are a few things that make them different from the reinforcement learning environments. So illegal moves is a big one. So the moves that are valid at a particular turn will depend on the state, and that's rather different from Atari, for example, where you can always go up, down, left, or right. Also, they may be turn-based. So other environments may assume that every player acts at every turn. As you'll see later, we do allow that, but in practice, we generally operate on turn-based games, so one player acts at a time. Then we also, as I said earlier, wanted to connect the various different research communities who may be approaching the same problems, but with different algorithms and different terminology. So part of the point of OpenSpiel is to allow those communities to collaborate more effectively. And then, of course, open code, open metrics makes it easier for us to talk about our progress and compare our work and build on each other's work. And lastly, just reproducibility. We wanted to be able to publish our research, publish our algorithms, allow other people to reproduce what we've done and build on top of it. So hence OpenSpiel. That was a very brief introduction to OpenSpiel. I'm going to continue, unless I have any questions, with a dive into some of the gory details of the API. Just a reminder that this link is still here. I'll just repeat this actually.
So I have one quick question, perhaps. We were actually looking at the OpenSpiel at some point and trying to also, I guess, integrate it with some more traditional multi-agent learning, which was taking actions at the same time. I think we were struggling a little bit with that at that point. Is that so? Is there support currently also for doing domains where the actions are not turn-based?
So yes, there is. So it's possible to have a game where every player acts at every turn. That's absolutely supported. However, many of our algorithms don't work on such games. So our implementations of standard algorithms often assume that it's a purely turn-based game. What we've done in practice when we've done research on turn-based games is we have an adapter that takes a simultaneous move game and turns it into a turn-based game, whereby the players act one at a time and then know that those actions are not revealed to the other players until every player has chosen an action. So in practice, that's how we've been doing it, is writing algorithms that operate only on turn-based games, but then turning the simultaneous move game into a turn-based game. However,
I see.
It would be possible to write an algorithm that operates directly on simultaneous move games, and we do have a couple of algorithms that operate in that mode as well.
Yeah, it just seems very worthwhile. I suppose if you can easily deal with just both kinds of games, but it's nice to hear that is possible, at least with a workaround.
Great, thank you for the question. Here's a very brief API example. We'll go into most of this in more detail later, but we are very definitely aiming for something that is easy to use from Python. So if you have a look at this example on the right in the box, you can see that we start by loading a game on the first line. We start by getting then we get the initial state, and then we're just going to mutate this state in place. In this case, it's going to say while the state isn't terminal, get the legal actions for the state, and either sample one of the chance outcomes, or alternatively, just take the first action from a list of legal actions. And so that will play a single episode of this game to termination. And the chance events are just treated as moves by a chance player. It's like an additional player of the game. And the player events of either player, in this case, it just picks the first action. It's not perhaps the most interesting trajectory, but that's what that does. I think I've said some of this before, but I'll mention it again, that the core of the library is C++ with a Python API and also a Julia API and a Go API. So games are primarily implemented in C++. We have recently added the ability to implement games in Python. So that is a little limiting in some cases. If you want to do, say, a Monte Carlo tree search, for example, then the fact that moving from one state to the next involves some Python code will slow you down considerably. But if you're doing a different kind of algorithm that maybe just extracts the game tree at the start and then does all of its processing by analyzing a game tree, then the fact that the game is in Python doesn't really hurt you very much at all, because you're just doing a single pass through the tree. So depending on what you want to do, a Python game implementation can be okay. Again, algorithms are in C++ and Python typically. And we also have lots of examples and an increasing number of collabs. Hopefully, at least some of you are looking at a collab right now to demonstrate how these things work. The key abstraction that we use in OpenSpiel is this state abstraction. And this is a world state. So what that means is it takes into account all the information that's available to both players and also information that may be hidden from both players at the moment. So it's the full state of the world, the state that a simulator of the game would have to have. So that means that algorithms need to be somewhat careful that they can't, if they're past the state, they have more information than a player would actually have. So they need to be careful only to depend on, for example, the observation that a player would have of the state, or what we call the information state for a particular player, which is the information that they're entitled to, and not the full identity of the state. Also on the right, shown we have our general game. We also have a simultaneous move game, which is a particular kind of game, and a normal form game, which eventually we have a matrix game down here as well. So we have various special cases of games where more methods are available, but in general, most algorithms, most of the time, just operate at the level of a game and a state. So I'm going to, almost every game in OpenSpiel has a playthrough. So that's a transcript, essentially, of playing a single episode of the game. These we use as tests, so we verify that when we make a change, it doesn't have any unintended changes to the playthroughs. And they're also an extremely useful way to understand how the game works. So I'm going to start by going through a few of these fairly quickly. This one is Tic-Tac-Toe. So you see the playthrough starts by giving you various information about the game. So it's deterministic, sequential, that's instead of simultaneous move. It has perfect information, 2 players. The rewards are only at the end of the game. There are no rewards during the game. And it's a zero-sum game. So that's kind of basic information on Tic-Tac-Toe. And then there is some information on the action space. So there are 9 possible actions, 1 for each cell. The utility ranges from -1 to +1. And we have an observation tensor, which is shaped 3 by 3 by 3. And we'll see exactly what that means in a moment. So here's, we'll have a complete playthrough. Obviously, it starts with the board being empty. There it is. This is the initial state. So the board is empty. And obviously, that's not terminal. And you can see in this initial state, the legal actions are 0 through 8. So it will be legal to play in any of the 9 cells of the board on the first go. And then these actions are in string form as well. So because we want to be friendly to neural network type players, we typically number the actions in a fairly dense way because they're likely to be the output of a neural network head, for example. So here they're just labeled 0 through 8. And then we have this translation into a string form. And I'm just going to talk about the observation tensor. So you can see them here. There's a different observation tensor for player 0 or player 1, although because this is a perfect information game, they both have the same information. The way this one is structured is it's 3 by 3 by 3. So the board is 3 by 3, and then there will be a 1 either in the first channel, which corresponds to an empty cell, or the next channel, which corresponds to player 0, or the next channel, which corresponds to player 1. And in this representation, just to make it a bit easier to read, zeros are denoted with this empty circle and 1s by this built-in circle. But in general, the observations could be any floating point value. We generally try to use 0s or 1s. So that's the initial state. And then in this particular case, I should say this playthrough was generated at random, so you're not going to see very high quality tic-tac-toe here, just warn you in advance. So the first move is action 8, which is player X playing in the bottom right corner, and you can see that there. And now you see the observation tensors are updated. This bottom right corner is no longer empty, but it's occupied by player 0. And you can see that the legal actions have reduced. So playing in cell 8 is no longer a legal action. And so here's the next move, played here. The observation tensors have updated, and the legal actions again, action 3 has been removed from the set of legal actions. And so we go through the game. I think this game is eventually won. There you go. At the end of the game, X has aligned at the right-hand side. So you can see that the game is over, its terminal is true, and the rewards and the returns both show +1 for player 0 and -1 for player 1. The distinction between these two, by the way, is that the rewards are potentially things which you get every step. So that's the typical reinforcement learning idea of a reward, that you take an action and maybe you get a reward, whereas the returns are the total over the entire game. So that means that if you have an algorithm which is capable of taking this step-by-step information, you can just look at rewards. But if your algorithm just needs a value for the entire game, then you can look at the returns instead. Okay, so that was Tic-Tac-Toe. I'm just going to do a couple of others very quickly. This one is rock, paper, scissors. So this is now a simultaneous game. And you can see that the action here that is taken is actually it's described as a joint action. So there's an action for player 0, plays scissors, and player 1 plays rock. And the action, rather than being a single integer, is now a list, 1 per player. And this is just a one-shot game, so the next state is the terminal state, and the rewards are that rock beats scissors, so player 1 is the winner in this case. I'm just going to go Pig, which is a very simple dice game. The new thing here is that we have a chance player. So the dice are a stochastic event. We support two kinds of chance. So one is a sort of sample stochastic, is what we call it, which just means that the transition from one state to the next is stochastic. We generally try not to use that. Instead, we prefer this explicit stochastic, which means that there is a chance player and their move represents the chance outcome. So the roll of the die in this case. The reason we prefer that is it means that the chance events are actually in the game tree, and so we can analyze the complete game tree. Whereas if we just have a stochastic transition, then all you can do is sample it, which obviously restricts the class of algorithms that you can use. Okay, I'll get to a stochastic outcome. Here we go. So this, the player decides they want to roll a die, action 0, and then we're now in a chance event. So chance event is true. That means the current player is the special value of -1, which is the chance player. So it's not any of the regular players of the game, but the chance player. And the chance player can take these actions, 0 through 5, so that corresponds to die rolls of 1 through 6. And you can see that we give each of them a probability here. So they each have a probability of 1/6. And then in this particular case, it was a roll of 2. So that's how chance is handled generally. Lastly, we'll come back to Coon Poker later in more detail, but this is an imperfect information game. So there is information which is available to one player but not the other. Each player has a single private card the other player doesn't see. So that's reflected in a number of ways. So we have a look. The game starts with a couple of chance events to deal the cards. And here we are. After those have both happened, the deal has been made. So the first player was dealt card 1 and the second player card 2. Then if we have a look, for example, at the information state string, you can see player 0's information state is 1. So they get to see their card is a 1, but they don't see the opponent's card. And likewise, player 1 gets to see their own card as a 2, but they don't get to see the card of the other player. That is also in tensor form here for neural network type algorithms. Again, you can see that private card for player 0 is indicated, and the private card for player 1 is indicated, but neither player gets to see the private card for the other player. All right, that's a very brief overview of what games look like in OpenSpiel. My main recommendation here is if you're planning to work with a particular game in OpenSpiel, start by reading the playthrough, because that will give you a really good idea of the game dynamics and how the game works. And equally, if you want to implement a new game in OpenSpiel, then create a playthrough early and then read through it carefully and make sure that it's doing what you think it's doing, like what you intended it to do. It's a great aid for debugging and understanding. Right, I'll pause there for any more questions.
And maybe I have a short question. Does OpenSpiel also support continuous action spaces, or is it all discrete actions?
Yeah, we only support discrete action spaces. So we have given some thought to how we might do this, but we're not there yet.
Cool, thanks.
Okay, so I'm going to move on to talk about Coon Poker, and we're going to implement CFR on Coon Poker simply. So I imagine many of you know what it is, but just bear with me while I explain it. So it's a very, very simple form of poker. It's played with a deck of 3 cards. So the 2 players get 1 card each, and there are only 2 actions, pass or bet. And the longest possible sequence of actions is for the first player to pass, the second player to bet, and then the first player has to choose whether they call or fold at that point. And that is it. So the maximum episode length is the 2 chance events to start with, plus 3 betting actions. And the number of decision points in this game is only 12 distinct decision points. So it's a really small game, but it's still interesting to use as a kind of hello world to test algorithms out on, which is exactly how we do use it and how we'll be using it later. So I touched on this earlier, but the information state for a particular player is their sequence of observations. It's kind of the summary of all of the things that they've observed over the game so far. So here we have what an observation state might look like, is that both players have contributed 1 chip to the pot. We've been dealt the queen, and our opponent has bet. So that would be a typical information state. It contains those sets of information. And the fact that we have the queen is, of course, a private observation. So our opponent isn't privy to that information. I touched on this again earlier, but it's worth repeating that the world states and information states are different abstractions, and the world state is a much finer abstraction than the information state. So the world state will include the kind of product of the private information of both players, whereas an information state will include the private information only of 1 player. Yeah, here we are. So the information state, the world state contains the full history. So that's the actions of both players and also the actions of this chance player as well. We've done this already. Have a look at the playthrough of Coon Poker. I think maybe let's have a look at it again and just get the details of the game mechanics, make sure we understand those. So this is a really short game, as I say. In this particular case, we start by dealing a card to player 1 in state 0, and the action that takes place is deal 1. So they get the queen, the middle ranking card. We then deal an action to deal a card to the second player. They get a 2, so they have the higher ranking card. So the second player has the higher ranking card. And now we go on to the betting. So in this particular case, the action that's chosen is the So the first player has the choice of either passing or betting. They choose to pass. And then this is how we represent these states. So these, the 1 and the 2 is we'll see a few of these later, is why I'm belaboring it now. The 1 and the 2 is the private deal, and the pass is the action that's happened. But you'll see that from a particular player's point of view, they just see their own card, either the 1 or the 2, and the action, the pass, which is obviously a public action. And the next action is a pass, so it's not a particularly dynamic game, this one. So overall, both player 1, 2, and both players pass. Again, you can see the information states. The players just get to see their own card plus the 2 bets, the two passes. And as we said, the second player has the higher card, so they receive a reward 1, and the first player is a reward of -1. This is a poker game, so it's settled by money rather than by win-loss. So in the case that there is a bet, then the stakes are higher. So you would be +2 or -2 if there has been a bet that has been called, and +1 or -1 if it's just the initial antes that are in play. Okay, so that's Coon Poker. We're going to do quite a bit on Coon Poker, so if anybody has any questions about it, now would be a good time to ask. Excellent. I should assume that everybody is entirely happy with it. So what we're going to start by doing is implementing a very simple CFR algorithm. So I should say that OpenSpiel already has, in fact, several implementations of CFR. So there is no reason to do this other than for demonstration purposes. And the version that we're going to write now is very simple and omits lots of error checking and robustness and logging, and also omits the various subsequent variations to the CFR algorithm that improve its performance. So we're just going to do a very simple CFR implementation. Here's the algorithm we're going to implement. Starts by initializing to a uniform random policy, and then repeatedly computes the counterfactual regret for each action at each decision point, and then updates the current policy at each decision point to be proportional to the total counterfactual regret so far, if the regret is positive. If the regret is negative, then we don't take that action. And then at any point, you can stop, and the policy that we're learning is the average policy across all iterations of this loop. So not the current policy that comes from regret matching, but the average policy. Okay, I'm going to switch to my Colab at this point. 1 second. And now we're on to the interactive bit. So I'm just check that. Can I just check this is visible and easy to read, is it?
Yep.
Yeah, great, thank you. So we'll start just with, again, some introductions to how OpenSpiel works. So this is just a very simple player game of tic-tac-toe. So it loads the game, gets an initial state, and while it's not in the terminal state, picks a random choice from the legal actions. So that should give us a game of tic-tac-toe, and indeed there it does, it was a draw. We, however, are going to play Coon Poker. So we load the Coon Poker game, and then we have a look at the various attributes. So none of this should be surprising. Sequential game, explicit stochastic. So that means that the stochastic events actually appear in the game tree. It's imperfect information, zero sum. Rewards happen only at the end of the game, and we are doing a 2-player version. Our version of Coon Poker does also generalize to more players. I'm not sure how interesting a game it is with more than 2 players, but we do support it. Then a useful thing for doing this kind of investigation is to have policy. So we have going to use the Spiel policy lib here and just create a simple tabular policy. So what this means is that for every decision state, we have a pair of probabilities. So the first one is the probability of taking action 0, which is pass. The second one is taking action 1, which is bet. And this list here of probabilities is in this order. So these are all the possible decision states. And just to remind you, something like 2 PB, that corresponds to being the first player. You're dealt card 2, that's a king. You pass, you hear your opponent bet, and now it's your go, and you have to decide whether to call that bet or to fold. So that's a representation of that particular decision point. And in this case, we've said all decision points are just 50-50. So because I'll need it later, this is just a simple printer that makes this a little bit more readable. So you can see each of the decision points, and then for each of them you have the policy. So here again, 50-50 pass or bet in each case. So once you've got a policy, you can pass it into the various tools we have. So we have an exploitability calculation. There you go, 0.92. This is actually Nash-Con rather than exploitability. So this is a slightly more general notion. What it means is that we replace each player in the game with a best response, and then we look at the total score that best responder gets when totaled over all of the seats in the game. So in this particular case, with 2-player zero-sum game, the Nash-Con is just twice the exploitability, but it's something that generalizes to multiplayer games, non-zero-sum, rather more conveniently. So this is not a great strategy, therefore, uniform random. So on average, you'll lose 0.92 chips in the game. So let's try and find a better one. So here's our CFR implementation. It starts, so there's just a utility function here. The CFR algorithm relies on maintaining reach probabilities. So I'm going to represent those as an array of probabilities, one for each player, with the last one being the chance player. So there'll be 3 probabilities in total, 1 for player 0, 1 for player 1, 1 for chance. And this utility function here just takes in one of those arrays of probabilities and a player and a probability and just updates it by doing that. That just makes the rest of this slightly easier. Okay, so here's the actual implementation of CFR. So this function takes in a state, so that's an initial state that we're starting the analysis from, the kind of root state, and the reach probabilities. So the probabilities for each player that we get to this state under the current policy. So again, that could be the chance probability of getting here, or the reach probability for a particular player. And then what we're going to do inside this function is update our regrets and return the utility for all players. So we return the utility because this is used recursively and we need to know the utility, and we update the regrets as we go. So there are 3 cases here. Here's the first case. We just say if the state is terminal, so if the game is over, then we just return the returns. So the utility for all players is returned in that case. Then the next case is a chance node. Again, in the case of a chance node, we don't have to update any regrets. We just need to return the utility. And so we do that just by looking at the chance outcomes for the state, which gives us a list of the possible chance outcome or chance action and the probability. And then we just return the sum of the probability times the utility of the child node. So we're doing 2 things here to find the child node. We're doing state.child action. That is the subsequent state. So when we were looking at this earlier, we were mutating states in place by doing apply action. Here instead, we're doing state.child, which gives us a new state, which is the child state of the state we started with. And then the new reach probabilities, here they are. So we're updating player -1, which is the chance player. Here we're kind of abusing maybe a bit of Python notation, which is that the Python index of -1 means the last element of the array. So we can use our -1 for the chance player and just have chance at the end of our vector of players, which is either nice or horrible, depending on your preferences. And we update the chance vector with that probability. Okay, so now we're at the meat of the algorithm, where we actually have to compute the regrets. We need to know which player we are, so we can just ask the state, what's the current player. So here, for example, is where the assumption that we're in a turn-based game is kicking in, because in a simultaneous move game, there would be no such thing as the current player. And we would have to do this rather differently. I'll touch on that in a moment. And then we need to get the index of the current state into the policy. So if you remember, the policy had 12 decision points in it. So we're saying for the current state, which of those 12 decision points does it correspond to? So this is the bit where we throw away all the privileged information that's in the state that we're not really entitled to know, and just map it back to a decision point, which means that the different states which a particular player can't distinguish will all be mapped to the same decision point here. Then we do compute the utility after each action. So this is very straightforward. We just go for each legal action. So
sorry, I think I missed what you were just saying there on this index line, and it actually sounded quite important to follow what is going on.
Sure.
Could you repeat or try to explain again? So somehow there, the information that is observed is filtered out, you're saying?
Yes. So if you remember, the policy here has, there are 12 decision points shown here. So there'll be multiple states for each of these decision points. So this, for example, we've been dealt a 2. The opponent could either be dealt a 0 or a 1. So there are 2 actual state objects, states of the world, that correspond to this same decision point. So the index will take in either one of those states and return index 6 or whatever it is, this index into the policy array.
So you take in the actual, say, game state and you map it to an index of information set, essentially, yeah?
Yes, exactly so.
I see, yeah. That makes sense.
Cool, thank you for asking. So yeah, that was here. Then here, we go over the legal actions. We get the probability of taking that action. And this is where we're using the index to index into the policy. So we get the probability that we take this action. And then we compute the utility of that action with a recursive call, which will also update the regrets in the rest of the tree. And now we update our regrets. So the counterfactual reach probability is the reach probability excluding us, but including chance. So we can do that just by doing this product here and excluding the current player from this product. Oops. Now we have the utility, which is indexed by action and player, and the policy, which is indexed by action. And we just do a sort of dot product type thing over those, and we get the value for each player. So now we have the value of this state for each player. And then the regret, we compute that for each legal action, and it is simply the counterfactual reach probability multiplied by the utility for this action for this player minus the value for this player. So that's precisely the definition of counterfactual regret. And then we've done that, we return the value of that state for all players. There you go, that's a CFR implementation. Here I can run it. Basically, in order to do that, I need to load a game, start with my uniform random start policy. Here's the root state, the initial state that I'm going to analyze. Here's my current policy, and my regrets start off by being 0. And at each step of my loop, I just do one of these CFR calculations and then find the new policy. So I take the floor of the regrets. I just choose to floor them at not quite 0 to avoid divide by 0 problems. And then the current policy just is updated to the normalized regrets. And then I also keep track of the average policy as I go. And then every now and again, I will evaluate the average policy using our Nash-Com calculation. I'll just demonstrate that it works. There you go. So if you remember, uniform random and Nash-Com about 0.92. As you can see, this goes down pretty rapidly, which is encouraging. And if you like to see a graph of that, there you go. The Nash-Com is going down very nicely. And as hopefully we know, it should be linear in log-log space, and there it is, a nice linear decay of exploitability in log-log space. We can also just check what policy we ended up with. So here it is. Here are the 12 decision points and the probability of each one. So you can see there are some fairly clear decision points. So if you've got the king and your opponent bets, well, you should definitely call because you've got the best possible hand. If you've got but on the other hand, there are some cases where you have to have a mixed policy. So if you have the jack, the worst possible hand, you have to bet sometimes. Well, you should probably bet sometimes. And actually, what should happen is you bet with a jack with some probability, here it's 0.21. You should bet about 3 times that often with the king. And you can see that would be 0.629, we're at 599, so pretty close. And also, there's a downstream consequence that if you check with the queen, you then need to call this probability plus a third. And again, you can see it's pretty close to that. So not only is the policy low exploitability, it has converged in policy space as well. So always close to conversion. Right, so that is implementation of CFR in OpenSpiel. I'm going to move on very quickly. It's taking slightly longer than I thought, to an implementation of reinforce. I think I should be able to get this done in 5 minutes, but we'll see. So this is even simpler. We start with the uniform random policy. So here we go. I'm going to skip over probably some of these, but the main function that does stuff is this generate trajectory. So this takes an initial state in a player, and it just repeatedly samples from our policy and appends state and action. So we get a list of state action pairs. If it's not our turn, then we just treat it as a stochastic transition. So it doesn't form part of the trajectory that we see for RL purposes. And that could either be a chance outcome, like dealing a card, or it could be the opponent taking an action. And that's not part of the trajectory. So I'll just show you what that looks like now. We have a fixed policy, which is just uniform random, and an RL policy, which we initialize as uniform random, and let's generate some trajectories. I'll run it just to prove I did it. So each of these trajectories consists of a list of pairs. So this is a state action pair and an overall reward. So we have a look at this one. We're at decision point 2, which means I think that we were dealt the queen, the middle card, and we made action 0, so we passed at that point. So it seems that our opponent must have bet, otherwise the episode would have been over. And that took us to decision point 3. So we still had the queen, and we had to decide whether or not to call the opponent's bet. We chose to call, and unfortunately that's the wrong choice. We lost 2 chips for that. So it appears that our opponent must have had the king. And you can see you can generate multiple trajectories like this. They're all going to be quite short because this is a very short game. So they'll all either be 1 or 2 choices long, but they're a list of state action pairs. Then the reinforced algorithm is really simple. You generate a trajectory and a reward, and then you take the logics of your policy, you update them by the reward. So if you get a positive reward, then the probability of taking an action will go up. If you get a negative reward, the probability of taking that action will go down. the amount by which it changes is given by this learning rate, which here is just a fixed 0.01. And then you do that manipulation in log probability space, and then you convert them back to probabilities. And that is it. That's the reinforced algorithm. So I'll run that. It should take a couple of seconds, just for 10,000 steps. And then we can evaluate it. So here I have an exhaustive evaluation. So again, it does in a similar pattern to what we've seen before. Terminal state is the returns to the player. If it's our move, then we look at our policy. If it's a chance node, we look at the chance outcomes. And if it's the opponent's move, we look at their policy. But either way, we get a list of possible actions and probabilities. And then the evaluation of the policy is just a weighted sum of all of the children weighted by those probabilities. And that enables us to evaluate the policy that we got. So here's the policy that came out of our reinforcement learning. And here's the score. So it got to 0.75, which is not too bad. You might remember that the optimal score against uniform random was 0.92. So we haven't quite got that. So the policy hasn't quite converged. I'm sure if we did more reinforcement learning, we would get there eventually. Actually, one thing you can notice is that there are some cases where this policy is clearly not converged. So here's an example. 2, you pass and bet. So you've got the best possible hand. You've passed, your opponent has bet, but it's still not certain that you should bet at that point. So it's giving only a 74% chance of that. It will converge eventually, but RL takes a long time. What we can do actually is just convert this to the greedy policy. So just say, rather than playing these 2 actions with these probabilities, just pick whichever one is the best. If we do that, we get a much simpler policy, and we converge to 0.9, which we know is optimal. Right. I realized I forgot to do something that I wanted to do, so I'm just going to go back and do it, which is here, if we have a look at our CFR for Coon Poker, there it is for Coon Poker, but we can also, this is the point in a way, we can do it for other games as well. So the Duke Poker is a somewhat bigger game, so this will be a bit slower, but you can see exactly the same algorithm, just tell it to run on a different game, and there it does. Or to return to an example we were looking at earlier, one of the simultaneous move games that we have is, I'm going to reduce this slightly, OpenSpiel, or the game of cross strategy, which is a card game. So this is a small version of OpenSpiel, imperfect information, 4 cards each, 2 players. And if I launch this, it will fail. And it fails because the player is -2. That's our special sentinel value for simultaneous move games. And we were not expecting, our algorithm wasn't expecting that. But what we can do is just say, let's turn that into a simultaneous move game. So this turn-based simultaneous game just translates a simultaneous game into a turn-based one. And once we do that, then we can apply our standard turn-based algorithms to the simultaneous move game. And as you see, learn to play OpenSpiel as well. Right. I'm done. I have to say I wasn't entirely confident I was going to get through all that in time, but we did it. We managed to apply CFR to 3 different games and also learn a best response with reinforcement learning. So if that isn't a great advert for OpenSpiel, I don't know what is. Any more questions?
First, thanks, Ed, for the talk. I guess we do have a couple minutes for questions if people have questions. You can unmute yourself, I guess, if you have a question, or you can type something in the chat box and we can read it out. I guess I can get us started then if there's no other questions right away. So I'm trying to think about like what classes of problems this fits the best with. So it doesn't seem like a good fit for instance, deep multi-agent reinforcement learning problems. There's other classes of problems, I guess I can think in my head, but if you have a good way of describing the class of problems that and class of algorithms that you think are the best fit for OpenSpiel, that would be cool to hear.
Yeah, I would say we definitely have done some deep multi-agent stuff with OpenSpiel. One of the things I quite like about it is that you can try an algorithm in a kind of tabular way on a really small game, and then implement an approximate version of the same algorithm with deep neural networks, and then verify that it works on a small game, and then try and scale it up to very, very large game. So we absolutely have done that. So some work I did myself over this last summer was on Bridge, the card game, which is pretty big game, and we use reasonably large neural networks there, with some success. So that definitely can work.
So okay, so that yeah, I guess I'll have to take a look at it in more detail, because I wasn't clear whether some of the things that you were talking about here, like for instance, defining the information sets. If you're using a neural net, you want to learn those. You don't want to just predefine those. But maybe there's a way of doing that just, it's hard for me to get in the very quick overview that you can give in this amount of time, obviously.
Yeah. So the way we generally approach this is that the information state is kind of. So there are two ways you can do it. So one is that you can provide the full information state as as something that's available to the algorithm. So that's something that summarizes the entire history of the game so far. And in some games, that's quite natural and easy to do. So in Bridge, for example, that works quite well because the information state can just be your own personal cards plus the actions so far, which is not not a particularly large space. In other games, so something like Stratego, for example, it wouldn't be feasible to have the entire information state supplied to the neural net, you're right, because that would have to be the entire history of the game. So instead what we do there is we make the observation, the current observation, available to the neural net, and then the learning algorithm, as you say, would have to have some kind of memory and be responsible for aggregating its observations into some kind of representation itself. But yes, you can absolutely do that. So we by default, most of our games expose both of those if they can. So both an observation, which is just the current turn, and maybe if the game is small enough, then an information state, which is the aggregated thing over the history.
Yeah, very cool. Are there other questions? I guess we have a little bit of time.
Yeah, perhaps following up on that. So then, if I understand correctly, some of these conversions that you were doing, like this looking up which information set index for, say, a global state index, these kind of things are more optional in a sense than I presume, right? Because, well, so when we were working on this MADP toolbox, I'm not certain if you ever saw that, but we had this toolbox for DAC-POMDPs. This was one of the, the typical bottlenecks that we would run into when we started getting to, say, Horizon 7 or something. The number of action observation histories will become huge, and then doing these conversions, everything, kind of like came to a halt, or roughly, I guess, at Horizon 7. But
yes, I mean, exponential blow-up will kill you fairly soon. It's true. Yeah, so we have algorithms which are purely tabular in nature, which is what I was showing here, where, yes, you will be limited to fairly small games. But then we also have good support for functional approximation for deep neural networks. And those obviously can scale to very much larger games. So, I mean, we have an implementation of AlphaZero, for example, which is not the real AlphaZero. It's not as performant as the real AlphaZero, but it's definitely capable of learning a game like Hex or Connect 4, for example.
Interesting, cool.
Very cool. I think we gotta end it there in the interest of time, but hopefully people will check out OpenSpiel. It looks very cool. Thanks again, Ed.
Thank you. It's a pleasure. Contributions very welcome.
Yeah, read about OpenSpiel, use OpenSpiel, and contribute to OpenSpiel.